Hello everybody, I'm Nick, and in this video I'm going to show you how you can write allocation-free C# that is very fast or as allocation-free as possible using the latest .NET and C# features. Now understand that the purpose of this video and why you should watch it is because you should know how to optimize for memory or speed if you need to. And this will only focus on one use case, but the tools we're going to use can be applied in many other use cases. You just have to try and think how you can adapt them. So keep in mind that even though many of you will think, hey, this is premature optimization, or I shouldn't actually be doing this right now, well, the truth is you should know how to optimize when the time comes to optimize. And for me, for example, this is my reality. I have to write code that is so efficient just because of the throughput I have to deal with. So it really depends on your use case, but you should know this type of stuff. If you like the type of content and you want to see more, make sure you subscribe or ring the notification bell. And for more training, check out nickchapsas.com. So let me show you what I have here, and I have quite a few stuff. So I'm going to start with the program.cs here. So here's our use case. I have a GUID, and I want to convert that GUID to a URL-friendly ID. And then from that URL-friendly ID, I want to put it back to a GUID to use in my application. This is very common. Many services do that type of thing. From a URL-friendly type of ID, as you can see right now on YouTube, or this one over here, this is a URL-friendly base64 encoded ID. And even though this is not the only approach, this is one of the most popular ones. And the reason why we do that is because it's very unlikely you're going to have a long GUID in a URL. It just doesn't look friendly. So people tend to shorten them, and also because it's less bytes to have that shortened, some people do that for efficiency as well. Now let me run what you see right now on your screen to see what we're dealing with here, because I need to put everything into context. So first we have a random GUID, right? So this is where we're starting. Then if you were to just convert that GUID to a base64 string, you end up with 24-byte string that looks like this. Now, the reason why this is a 24-byte string is because we know that these are ASCII characters, and it's 24 because that's how much the 16 bytes of the GUID are converted into a base64 string. Now, here's the thing. These two last equals in the end, those are padding. You do not need them. So we can basically just remove them from the end. And because we know that the size of a GUID is fixed, we can just reappend them when we do the conversion back into the code. So we can optimize, as you can see here, that they're missing that part of the base64 string. The other thing we need to do is that the plus symbol and also the / symbol that are part of a base64 string are not playing nicely with URLs. For that reason, plus is being replaced by underscore and slash is being replaced by hyphen. So with these three changes, we're making a short URL-friendly base64 string. And then from that string, we write something that converts it back to a GUID. How does that look? Well, let me show you. I've made this class called GUID there. Weird name, and then I have the toString from GUID and the toGUID from string. The implementation is something very basic that at the first glance might look absolutely fine. We're getting the byte array from the GUID because we need to pass it to the toBase64 string method of the convert class. Then we replace, like I said, slash to hyphen and plus to underscore, and then we replace the last two equals with an empty string. And then in the end, we do the opposite. We replace the hyphen and the underscore with the slash and the plus, and then we append the equals in the end. And then we bring this all together using the GUID from a byte array here. So that's what we're dealing with. And in case you didn't know, a GUID is 16 bytes, and those 16 bytes come from 4 bytes from an int, 2 and 2 from two shorts, so 4 bytes there, 8 bytes, and then 8 bytes individually. And the color coding here represents what each item here maps to here. It's just sets of 2, it's hexadecimal. You don't really need to know that, but I think it's good to know. Now, what we want to see first is benchmark this and see how efficient it is, both in memory and speed, to put it into context. So first, what I'm going to do is I'm going to go to the program.cs, and I'm going to comment everything here out. And I've already added a benchmark. So I have this GUIDer benchmarks, which has a constant and a static read-only GUID, and it just calls those methods to give me results both on memory and speed on how they perform. So what I'm going to do is I'm going to say benchmark runner.run, and I'm going to point to GUIDer benchmarks. That's it. I'm going to change that to release mode and run it. And I'm going to give it a minute to run, and let's see what we get back. So results are back, and what we have is the toGUID from string taking 80 nanoseconds and allocating 184 bytes of memory and then the toString from GUID taking 95 nanoseconds and 256 bytes of memory. Now, this might look insignificant, but actually, small things like this, if overused, can amount to a big amount of memory. Really, they can. So our goal here is to completely remove any allocation on the first method, the toGUID from string, and significantly reduce the second one, because we cannot completely eliminate it, because we eventually return a string, which is a reference type, allocate on the heap. What can you do? So let's go ahead and optimize those. So first things first, let's delete that and uncomment this because we're gonna need it. Right, so here we go. I'm gonna start with the second method, the one that returns a GUID, because here we can actually eliminate all the memory allocations on the heap. GUID is actually a value type because it is a struct, as you can see here. And even though we accept a string here, which is a reference type allocated on the heap, we can change that to accept a read-only span of character. And let's go ahead and create the new signature. So we want a public static GUID here to GUID from string OP for optimized. And this can now be a read-only span of character or char or car or whatever you call it, and call that ID here. And then this can return a new GUID, and we're going to implement that in the end. And the reason why this is acceptable and we don't break the API is because if I go to the program.cs and I say, for example, here, GUID again, OP, and add the OP here, this works because a string can be implicitly converted to a read-only span, and that's because strings are immutable and the span can use the arbitrary memory of the string to read the characters and do stuff with it. Right, so back in the method, the first thing that I know I'm going to need is a span of character. This will replace what normally we would use, which is an array, which would be allocated on the heap. Here, a span is not going to be allocated on the heap. It's a stack object. And for that to happen, I need to say base 64 characters. And I can say stackalloc to allocate on the stack 24 characters. And this will give me an area in the stack represented by this object, which I can play with without having to worry about heap allocations. I should also say here that this video will not be using unsafe code at all. No fixed, no unsafe, none of that. We could, but maybe that type of optimization is for a separate video because there are concerns around that. So what I know is that I'm dealing with 22 characters in that incoming ID. And the last two, the 23rd and the 24th, which I can represent here with 22, and 23, I know that those will be the equal symbol. So it would be that. So that's how I can add it, but I can also extract that into a separate constant and say private const char equals car equals equals, a lot of equals. And I can use it then like this. So what's left now for me is to assign from the incoming ID to the base 64 characters. So the only thing I need to do is replace the characters that are incoming. So the hyphen to the dash and the underscore to the equals. So to do that, all I want to say is base 64 characters I here equals ID I, and I have a switch here. And first I have the hyphen. So I could say something like this, and we will, but I'm gonna again extract it into a field. So that should turn into a /, and then we have the underscore that is turned into a plus, and anything that we haven't mapped is ID of I. Here we go. And this will now map everything we need here. Now, of course, I don't want to have this like this, so I'm gonna extract them in constant. So private const, so let me quickly do that. Private const character. So that's what it looks like. And now we need a few more things. First, I know that a GUID is 16 bytes in its GUID form. So I need a span of bytes, which again, I don't want to have an array here. I want a span of bytes because it's a stack allocation. And I can say ID bytes equals stackalloc. That's why it's a stack allocation. And I'm going to say byte array of 16. It's not really an array, it's 16 bytes in memory. And then eventually I'm going to use the GUID constructor that accepts a read-only span, as you can see here, which doesn't allocate any memory. And what I need to do to finalize this is write the base 64 characters of this span of characters into this span of bytes from 24 characters to 16 bytes. To do that, I can use the convert class and say try from base 64 characters. And first I pass down the characters, so base 64 characters, and this goes into the ID bytes. And then I do not need the last parameter, which is the bytes written, so I'm just discarding it. And now this is our method. If I go here, as you can see, this is our method. This is what we added. And what I can do is I can write it in the end. If I go ahead and I run this, watch what happens. Here you go, the GUID is constructed. Let's go ahead and debug this to see exactly what's going on in slow motion. So I'm stepping into the method over here, and we have this implicit conversion of the read-only-span, which is represented as you can see here. And then we step over this base64 span, which allocates 24 characters. And then we iterate over each item. We're mapping the ones that needed to change. In this case, we don't really have any that need change. So it's just the same thing. We append the 2 remaining characters. So that's what the final thing looks like. We allocate the 16 bytes here. And as you can see before the conversion step, everything is just byte 0 in that span. But if I go over that and I write into it, then every byte in that span is written, and I can step over this, and this returns the final GUID. So how does that look in terms of performance? Well, let me go ahead and duplicate this benchmark and add the OP at the end and run it and see how it performs. So I'm gonna say first return here because I want to return early, because I want to say benchmark runner dot run GUIDer benchmarks. Here we go, change this to release mode, and let's go. So results are back, and as you can see, 0 memory allocations. This will make a visible difference in your application if you're using this conversion a lot. And also it is more than half the speed. So as you can see, this has an impact. Not so much on the execution of the operation. I mean, it is half the time, but it's not like we're dealing with seconds here. But this memory, this will make a difference. Now let's go ahead and optimize the remaining stuff. And that is the toString from GUID. And there, like I said before, we can't really eliminate all the allocations because ultimately we return that string. So if we are constrained in safe code, which we are, we cannot use unsafe here. Let's see how far we can get. So I'm gonna go ahead and move this these fields up here. Here we go. And try to create the efficient version of this code. So duplicate that, say OP, keeping the signature the same. And I'm just gonna return empty here. And let's see what we can do. So a lot of the things will look the same. So we are fundamentally trying to do the opposite here. But the main reason why this approach has a problem, well, there's many problems here. First, we're allocating 4 strings here, but also we have this 2-byte array. And we're using that because we need to access the byte array behind the scenes in the GUID, and there is no as byte array or something. So when you have 2 will actually allocate the thing that it says it will. So if it's a 2 char array or 2 list or 2 something, 2 means I'm gonna allocate this thing again into that new type. If it says as, like as list, as enumerable, as queryable, those do not allocate the thing again, they just cast it behind the scenes. So we need to find a way to access the byte array without allocating the byte array again. How do we do that? Well, first I know that I'm gonna need 16 bytes. So I'm going to say ID bytes, and that's going to be a stackalloc of 16 bytes. Again, no heap memory here. And that's going to be for the bytes of this ID. Then I know that I'm going to need a span of 24 characters again on the stack. And the reason why I need that is because I'm going to have to convert the ID bytes to the base 64 characters here. Now, the first thing for this to work, like I said, is for me to find a way to access the bytes of this GUID without allocating a byte array again, because that's a heap allocation. To do that, I can use the memory marshal class. And again, this is all safe code, nothing unsafe here. And say try write, and I have a destination and a value. My destination that I'm going to write into is this span over here. And then I have the ID, and it needs to be a ref ID because that method needs a reference to the type that you want to pass into that span. They can't all be winners, but at least this means we can write into that span. And just to prove that this works, what I'm going to do is I'm going to do the same thing as here, URL friendly base 64 ID OP, and change that to OP, and then call that OP here. I'm going to stick a breakpoint and debug it and see what we get. So step into that. And as you can see, this starts empty, nothing in that span. And then I step over the mashup. And as you can see, actually the GUID is full. And then I'm stepping over the try write method. And now that ID byte span has the bytes of that GUID written into it without having to allocate 16 bytes of the GUID again. So that's great stuff here. Now I also need to write those 16 bytes in the span into the 24 characters of this base64 span. And to do that, all I need to do is say base64 dot encode to UTF-8 and say ID bytes here and then base64 characters here. And actually, now that I'm looking at this should not really be characters. It's not exactly the opposite of this. This at this point should be bytes. So base64 bytes here is what we should be dealing with. And this is actually what this method even accepts. And then I can discard the last two items here. So this and this can go bye-bye. And now if I do that, I'm going to write those 16 bytes into base64 24 bytes here. From that point on, it's just about doing the opposite replacement. So first we need our span of characters, and that's going to be the final characters equals stackalloc of HR. And then I need to do the same thing. So for 22 items here, I say final characters, get the I equals base64 bytes, get the item, switch. I love these switches. And then we have the slash, but in this case, it needs to be a byte. So I'm going to also create a slash byte here and change that to a byte. And to do that, I need to cast it to a byte. So slash byte, and the byte is converted into a hyphen. Here we go. And then I have the plus, and that also needs to be a byte. Surprise, surprise. So I'm going to change that to a byte, change the name to a byte, and cast this to a byte. Here we go. And I'm going to say plus byte goes into underscore. And then the remaining, here we go. We can cast that to a character, and it is whatever incoming base64 byte we are getting. Here we go. And now I can say return a new string and pass down the final characters as a span, and there's an overload for that. So this will allocate no memory again. I mean, of course, it's going to allocate the string, but not the parameter going into the method. And now with that, if I go ahead and debug this code, let's see what we get. So I'm going to step into that. And as you can see, we allocate the two things. Then I can step over the writing, and the base64 bytes are all written here. And then I'm going to step over all the iterations. I don't want to go through every single one of them. So I'm just going to stick a breakpoint and do a 5. And in the end, all the characters are here in that span, and we can return them back in a very memory efficient and fast way. And if I let this play, as you can see in the console over here, both conversions are correct, both from and to a GUID. How does that perform? Well, let me go back here and duplicate this benchmark. So I'm going to say this underscore OP and then OP here. And let's go ahead and run those benchmarks again and see what we get back. So results are back, and let's see what we have here. So as you can see, the optimized way is, how many times is that? 256 divided by 3.5 times less memory allocated, and it's 3 times faster. Again, the visibility of the speed of the execution depends on how many times you're using it, but the memory will have a very visible impact in your garbage collection. Now, does this mean that you have to go ahead and change everything in your code to be super optimized and use spans or whatever? Well, not really. You have to be very careful with how we're using those tools. For example, the stack has a maximum amount of memory, and if you exceed it, you're going to get a stack overflow. Now, it's highly unlikely that you're going to hit that 1 megabyte limit. I think it's 1 megabyte, but you do have to be careful. Now, let me know if you want to see more things like this, and actually let me know if you can make this even faster and more memory efficient without the use of unsafe code, because I can make it faster with unsafe code too. It's no biggie. I just want to know how faster you can make it with safe code. Well, that's all I had for you for this video. Thank you very much for watching. Special thanks to my Patreons for making these videos possible. If you want to support me as well, you're going to find the link in the description down below. Leave a like if you like this video, subscribe for more content like this, and ring the bell as well. And I'll see you in the next video. Keep coding.